All right, so today we are going to expand on this idea of the valence shell electron pair repulsion theory and get to where we can draw different compounds without having to look at the example or have seeing the formula or the structure drawn out already. Okay, so first of all, the first thing we have to do is we have to look at the amount of atoms that are involved. Okay, so we always know that there's one central atom and then there's going to be the terminal atoms, and this is going to be really important. Okay, so obviously if there's just two atoms here, there's only one structure that it can be. So diatomic molecules are all going to be linear because there's only one way that you can draw something linear. Now, the only thing difficult about a linear atom is figuring out if it's going to have a single, double, or triple bond. Yep. And so with hydrogen, we know that it only can be a single bond because hydrogen's full octet is an 8.
Right.
It's only 2 because hydrogen wants to be helium. Okay, so in this case, hydrogen will never, ever have a double bond or a triple bond. So hydrogen always is single bonded. However, fluorine still needs 8 electrons. And so in order to get him to have 8, we can't draw another bond here. We have to give him unshared pairs or lone pairs. So here, each line counts as 2. So we're going to give him 2 more here, which makes 4, 5, 6, 7, 8. So now fluorine's happy with his octet, and hydrogen is also happy with his 2 electrons. Okay? But when we start getting into a little bit more difficult ones, we have to think about that chart that we're learning, the VSEPR theory, the different structures that you can draw, molecular structures. So you always have to identify your central atom. That should be your first step. So step number 1, identify central atom. Okay, so it's pretty easy to see which one is your central atom because there's only one. Okay, so silicone we know is going to be our central atom. And so we're going to write Si in the middle. And then we have 4 of the chlorine. So if we look at our molecular structure sheet from yesterday, you can see that terminal atoms here, the one atom's bonded to central atom, this is the same thing as saying terminal atoms. There's only one that has 4. The rest of them have 6, 5, 4, and 2, 3, 2. So we know that this is going to be tetrahedral. Yep. So we come back here. We know it's going to be tetrahedral. We know there's one up, one out to the side, one coming out at us, and then one going backwards. Okay, so then now we just make chlorine. So you can see silicone is happy in the middle because he has 2, 4, 6, 8 electrons because each of these lines equals 2. Now we have to make chlorine happy. So we're going to put, because this is 2, 4, 6, 8, 2, 4, 6, 8. Okay. And then, so you would label this one, like on a test, we'd label this tetrahedral. And we would also say that these bonds, I made a mistake in the video last night. It was actually my 3rd time doing it here. These bin structures, they're out of order here. So that got me all messed up. So this is the 120 degree one. That's not the one I messed up on. But when we're talking about a bent molecule, these 2 here, these are going to be 104.5, and then this guy here and our tetrahedral structure right here are going to be 109.5. So you need to make that correction in your notes. Sorry about that. Okay, so this is tetrahedral, so this is 109.5. Okay, so that would be the answer there. All right, so here let's look at this one. Or let's go up here. Let's look at this guy. So we have our central atom, identify central atom, and then we use the VSEPR chart. Whoops, I forgot a P. The VSEPR chart to find structure. Is our second step. So our central atom now is selenium, and we go back. Which one has 6 terminal atoms? There's only one. So this is an octahedral. Oops, went back too far. Way too far. So it's octahedral, so we would label it octahedral. And we go 1, 2, and then 2 comes outward, and then 2 go back. Then we put iodine. Okay, and then of course, this is an expanded octet. That's why on the worksheet today this said it was an exception. We're going to be going over exceptions to the octet rule next week. So right now, octahedral and our trigonal bipyramidal are exceptions, and we'll talk about that Monday. But iodine still needs 8, so we have to put all these valence electrons on. I know you think it's a pain, and why do you need them? But otherwise, you leave iodine with 2 electrons, and that wouldn't be correct. Okay? And then all of these angles from here to here is 90 degrees. And from here to here is 90 degrees. All right. So now let's look at this guy. So now let's use our step number 1, identify the central atom, which is boron. And we have 3 terminal atoms. We go back, and there's 3. So it must be this guy. Or could it be this guy? As you can see, there's a couple that have more than one option. So then we get stuck. So that leads me to our next talk, our next slide, next thing we need to talk about. Whoa, that's not what we need to talk about. Here's what we need to talk about. All right, there is a calculation that will then help us figure out what we're supposed to do. Okay, so this is step number 3. This is what we do after we have identified our central atom and after we've looked at our VSEPR theory chart. Now we're just trying to narrow it down.
Right.
Yep. So now we write the number of one of the atoms as the given number. So we're actually doing a little bit of dimensional analysis. I told you guys this wouldn't go away.
Never gonna go.
Am I spelling this? Whoa, whoa, whoa.
Oh, wow.
Yeah. There we go. Sorry. Okay. So now we're going to write the number of one of the atoms as the given number. So our formula was BBr3. So we say how many boron there are. So we'd say 1 boron atom. Okay. So we would put 1 boron atom on bottom, and this is always going to be 1 on the bottom of your ratio because you want to know the number of valence electrons on top. So here we're just canceling out boron atoms. So we cancel out our units, okay? And then we put the number of valence electrons on top. So how many valence electrons does boron have?
3.
3 valence electrons, and I always label it Be negative because otherwise it just takes too much room. Okay, and then if there is another element, repeat that step again. So then we add this. Okay, so we're going to make a big plus sign, and now you put the number here. So now there are 3 bromine atoms, X in a line, and then 1 bromine atom goes on bottom to cancel that out. And it's always going to be 1 because in 1 bromine there are how many valence electrons?
7.
7 valence electrons. Okay, and that's all of them. So now we can equal this up. So I always make 2 little problems. I do 1 times 3 is 3 plus 3 times 7, 21, and that equals 24. Now, this is the total number of electrons that are going to be in your drawing. Okay? We want to actually divide this by 2 to tell how many bonding pairs, it could be a lone pair, it could be a shared pair, bonding pairs that we need. So we know we need 12 bonding pairs. Okay, so let me show you how this information is useful. If it is a trigonal pyramidal, it will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, if these aren't hydrogen, if these were boron or something else. If it is this one, it's going to have not that one, this one, it'd have 3, 6, 9, 10, 11, 12. So this one always has 12 bonding pairs. This one always has 13 bonding pairs, assuming that these are not hydrogen. If it's hydrogen, obviously it has 4. So we would now know that it's this guy. And you could even draw them both just to check. So, I mean, you could draw this like this, and you know you need 12 bonding pairs. And you can see right away you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you know that that is incorrect because there's 13 bonding pairs. So let's try it the other way, which is our trigonal pyramidal. Trigonal planar. Excuse me. And now we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you know this is the correct structure. Okay? And so this is our trigonal planar. And these angles are 120 degrees. Okay? So hopefully this helps you understand. If you didn't write all those steps down for the calculation, you can go ahead and pause it, and you can finish writing those. Make sure you know how to do this. This will be actually part of the quiz on Monday. We're going to do an activity, and we'll be drawing these all by ourselves, and make sure you memorize all the different structures, because this table here with the terminal atoms, the lone pairs, and the formulas and the structures are very important, especially the names, obviously. Okay? Have a good weekend.
Have a good weekend.
Nice.
Leave it in there.